So in this section, we're going to look at a few special factoring formulas or patterns to watch out for when you're factoring binomials. Bi means two, so binomials are polynomials with two terms. So one thing and then either plus or minus another thing. To introduce the first and probably most important of the special factoring formulas in this section, look at what happens when I multiply together two things that are almost the same, except that one of them has a plus and one of them has a minus. W plus 3 times W minus 3. If I use the FOIL method, W times W first is W squared. On the outside, I have minus 3W, and on the inside, I have plus 3W, and last, I have a plus 3 times a minus 3 gives me a plus or a minus 9, because a positive times a negative is negative. But these two in the middle, this minus 3W plus 3W, just add up to 0. They cancel each other out. So what we really end up with is W squared minus 9. So that's the multiplication direction, but if we were going the other way, starting with W squared minus 9 and trying to break it apart into one thing times another thing, that's what those things would be. One of them would be W plus 3 and the other would be W minus 3. So the kind of thing that's going on here is that we are factoring a difference of two squares. Difference means subtraction. Squares means something that is a perfect square. So it's either a variable squared, like x squared or w squared, or it is a number that is a perfect square, like 9 is 3 squared. Or it could have both of those things. So the formula to watch out for is a squared minus b squared can be factored into a plus b times a minus b. And here the a and the b just stand for whatever it is that's being squared. Could be a variable like x or w, could be a number like 3 or any of these numbers. So these are the numbers that are the perfect squares. These are the ones to watch out for when you're looking for that difference of two squares pattern. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. So let's say we wanted to try to factor x squared minus 100. Do you see how that fits this pattern? The first thing is x squared, so it's something squared. And the second thing is the number 100, which is 10 squared. So this fits this pattern where we've got the part of A being played by x and the part of B being played by 100. So x squared minus 10 squared. And so the rule says that this factors into two factors that both start with x and end with 10. It's just that one has a plus and one has a minus. So x plus 10 times x minus 10. And if you wrote them in the other order, if you put the x minus 10 first and then the x plus 10, that would also be correct. It's the same two things, and when you're multiplying two things together, it doesn't matter which one's first and which one's second. So let's try another one of these. Factor 9x squared minus 49. Everything here is a perfect square. 9 is 3 squared. X squared, of course, is x squared. So together that would be a 3 and an x squared. And then the 49, it would be 7 squared. So this is 3x being squared minus 7 being squared. So the a and the b would be 3x and 7. And so what are the two factors that this breaks up into? One of them would be 3x plus 7, and the other would be 3x minus 7. What about this one? 16p squared minus 81q squared. Everything here is a perfect square. 16 is 4 squared, 81 is 9 squared, and of course the variables are squared. So this is 4p all squared minus 9q all squared. So what are the two factors that breaks up into? One of them is 4p plus 9q, and the other one is 4p minus 9q. If you multiplied this back out, you would get 4p times 4p, there's your 16p squared. The thing on the outside and the thing on the inside would be exactly the same, except one would be minus and one would be plus. So they would add up to 0. They would cancel each other out. And then you have the plus 9q times the minus 9q, which gives you the minus 81q squared. Now, what about this? Is this a difference of two squares? Does this fit this pattern? Well, neither one of these numbers is a perfect square. 27 isn't just something squared, and neither is 3. But I see something we can do with this. Remember when we were talking about factoring out the greatest common factor? So there is a common factor for these two terms, and that would be 3. These are both 3 times something else. This would be 3 times 9y squared, minus this would be 3 times 1. So we can factor out a 3, write it as 3 times 9 squared minus 1. And now the part inside the parentheses, the 9y squared minus 1, is a difference of two squares. So can you see how that factors? We still have the 3 out here, but then the 9 squared minus 1, that's made up of a 3y being squared and a 1 being squared. So one of the factors is 3y plus 1, and the other factor is 3y minus 1. How about this one? Negative 25 plus t squared. Is this a difference of two squares? Is this the kind of thing we were talking about? Well, there's a plus in the middle, not a minus. This isn't really subtraction, or is it? There is a minus in front of the 25. So if we put the t squared first, plus the negative 25 second, we could say that's t squared minus 25. So now it is a difference. It's one thing minus something else. T squared minus 5 squared. So we can factor that into, do you know what the two factors are? By now you should have the hang of this. T plus 5 times t minus 5. Now if neither one of these had a minus in front of it, if it was just a positive 25 plus a positive t squared, that can't be factored. That does not fit this difference of two squares pattern, and there's nothing we can do to make it fit. Okay, so that was probably the most common and most important of the factoring patterns we're going to be looking at today. But I am going to show you two more that are a little more complicated, but they also are something to watch out for when you see a binomial and you think you might be able to factor it. And that is the sum or difference, so this could be plus or minus, of two cubes, two third powers. So here the factoring rule is a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. And the reason it looks like this, the reason it has to be this way, is because this is what it takes to multiply everything out and have you wind up with this. If we multiply all of this together, we get a times a squared, that's a cubed. We get this a times minus ab, so there's minus a squared b. We get this a times b squared, so there's plus ab squared. And now we're taking the b times each of these three things. So b times a squared, that's plus a squared b. b times minus ab, so minus ab squared, and b times b squared is b cubed, and some of this stuff in the middle cancels out, and what's left is a cubed plus b cubed. So that's for a sum of two cubes, and then a difference of two cubes. If there's a minus here, it's almost the same formula, except there's a minus here, and then there's a plus here. So the sign here matches what we started with, and the sign here is the opposite of that. And so what we're watching out for, the perfect cubes are these numbers here, 1 and 8 and 27 and so on. Like 27 is 3 times 3 times 3, so it is 3 cubed. So to factor u cubed plus 1, we've got a variable to the third power, plus we've got 1, which would be 1 to the third power. So this is like a cubed plus b cubed, where a is u and b is 1. So fill in u in place of a and 1 in place of b in this formula. U plus 1 times u squared minus 1u plus 1 squared. And then, of course, 1 squared, 1 times 1 would just be 1, and 1 times u would just be u, so we can simplify this a little and write it as u plus 1 times u squared minus u plus 1. How about another one? This is a little more complicated, but it is a sum of two cubes. The numbers 8 and 27 are both perfect cubes. 8 would be 2 cubed and 27 would be 3 cubed. And then we've got x cubed and we've got y cubed. So the first thing is something to the third power, the something being 2x. And the second thing is also something to the third power, that something being 3y. So just fill in this formula here, but in place of a, put 2x, and in place of b, put 3y. So we're doing to 2x and 3y what this formula says to do to a and b. 2x plus 3y times 2x squared minus 2x times 3y plus 3y squared. And since 2x squared means we square both the 2 and the x, we can write that as 4x squared. When we multiply out a 2 times an x times a 3 times a y, that would be 6xy. And when we take 3y and square all of that, 3 squared is 9, y squared is y squared, so there's our 9y squared. So here's what we have. 2x plus 3y for the first factor times 4x squared minus 6xy plus 9y squared for the second factor. Now this was a sum of two cubes. It was addition. We started out with a plus sign, so in the factors we had a plus sign here and a minus sign here. If this had been a minus, 8x cubed minus 27y cubed, then we would have had minus in the first factor and plus in the second factor. But everything else would follow the same pattern. So at least make sure you really know and are good at doing that first thing we talked about, the difference of two squares. And then next level up would be this sum or difference of two cubes. One more, 2x cubed plus 2,000. Start by factoring out the greatest common factor, which is 2. And now we have a sum of two cubes. We have x cubed plus 10 cubed. So that part factors into x plus 10 times x squared minus 10x plus 10 squared, which is 100. So our final answer here would be 2 times x plus 10 times x squared minus 10x plus 100. The 2 we factored out as a common factor, and the x cubed plus 10 cubed broke up according to this pattern as x plus 10 times x squared minus 10x plus 100.